Software Engineering Radio Episode 12, Concurrency, Part 1. Hello everybody, welcome to this new episode of Software Engineering Radio. This is the first of several episodes on concurrency. However, before we start with the topic, we have to make sure that we announce the winner of the book as a reward for the feedback you give us. And the winner of the Remoting Patterns book is John Rodley. We'll contact you, John, in the next couple of days or weeks to make sure we ship this book somehow to you. Please continue giving us feedback. If possible, give us the feedback through the comments facility on the se-radio.net website so other people can see what you think about the podcast. So let's get on to the topic, concurrency. This first episode is handled by Michael and Alex.
The idea for this episode stems from listener feedback, and it's on the foundation of concurrency.
We will lay the very basics in this episode. The following episodes will deal with more advanced topics.
So, what does concurrency in software and in software development in general mean?
Basically, it means that we have a computer that does more than one thing at the same time. In the simple case, of course, more than one application at the same time. Concurrency can be achieved physically, which means we have more than one hardware execution unit, more than one CPU, for example, such as in modern multi-core CPUs or server machines. But it also means that it's simulated through software, where concurrency is not real concurrency, where some things happen at the exact same time, but it's the switching between the applications is so fast that we get the impression of really concurrent running threads or applications. Almost all modern operating systems offer support for multitasking and multithreading, which is the basic of concurrency. We will deal with the terms a bit later and define them. But also infrastructures like application servers, virtual machines offer concurrency support. So we have it in different layers of the stack, infrastructure stack today. This means for programs that we have to deal with concurrency, we have stuff like threading libraries, pthread library, for example. We have to fork processes to get concurrency. So there are APIs to create new processes, threads, and to deal with concurrency issues.
Yeah, we asked ourselves, so why is it important? Why is concurrency today so important? And we discovered two reasons for that. The first is performance, and the second is scalability and efficiency.
Yeah, and performance is, of course, the most obvious. You have a task that just takes too long for one single machine to compute. There are the classic examples like weather simulation, where a single CPU is just not fast enough to deal with a huge amount of stuff to do. So we have to deal with this problem. We have to find algorithms that divide the problem into smaller parts to make separation on different CPUs possible, to use multi-CPU cluster systems so that the results can be computed in parallel. For this, you have to find new or different algorithms that solve the problem in parallel. Otherwise, you wouldn't get a benefit from other additional CPUs. So that's a pretty complex topic. Beside the weather examples, you can find this in financial services, for example. There are huge simulations running that simply would take too long on a single CPU, so the algorithms have to be factored or written differently to support multiple CPUs. If you just want to get a feeling for this, try to compare the different sorting algorithms, a bubble sort, a merge sort, a quick sort. How could you split it or redesign them to run in parallel on different CPUs? It's not a very trivial problem, it's actually pretty hard stuff. Fortunately, a lot of problems are symmetrical or parallel by nature. If you take the multi-user stuff, you can easily parallel the single tasks per user. You don't have to find a new algorithm to solve the problem, or a lot of graphical programs are easily parallelizable, like ray tracing, for example. You can easily put this on a multi-core or multi-CPU machine, but that's just for performance. We also have scalability.
Regarding scalability, the idea is to split the application and put it on several CPUs, or even to use one CPU more efficiently. And the problem with efficiency is that the CPU has nothing to do while we wait for user input or network input or disk I/O. And for this, it's a good idea to design the application using concurrency so that we can make best use of the CPU resources, not wasting time while we wait for I/O operations.
Yeah, exactly. We also have to deal with a different problem, or an additional problem. The speed increase of modern CPUs will not only be reached by simply raising or increasing the clock speed. This gets more and more difficult because we have physical limits there. So most or all modern CPUs have some kind of parallel processing in it, and you heard all the buzz about multi-core CPUs, and that's another thing you have to deal with as a programmer, because you have to really program or write your program that the different cores are used. So there is a very, very good article on this, and you can find it on the web, and we put the URL on our website. The free lunch is over, which describes exactly that problem, that modern CPUs will not get the speed increase simply by higher clock speeds, and that you as a programmer have to deal with it, that we have to, or that concurrency and programming for concurrency gets more and more important the next years. So before we go to the real programming issues and how you have to program it, I guess we should clarify some terminology, some terms. And the first are, or the very basic terms are multitasking, pre-emptive multitasking versus cooperative multitasking. When concurrency was introduced, most computers still had one CPU, but the applications had to wait very long for I/O operations to finish, because CPUs always were a lot faster than the I/Os typically. Operating system programmers introduced first multi-programming and then multitasking to deal with the problem. As Michael already mentioned, you can better use your CPU resources if you don't have to wait for I/O by just using the CPU for other stuff. So multi-programming was a very clever idea. To do this, the operating system has a scheduler which switched between the different tasks, and it did this so fast that they seem to run in parallel. Actually, they didn't run parallel because you just have one CPU, but it seemed like they were running in parallel. First, then we had some kind of cooperative multitasking, where the tasks have to set themselves asleep if they did an I/O operation, for example, or if they just were ready to wait. And so the single programs did cooperate and free resources for others to run. You might remember earlier Windows versions that had this kind of multitasking implemented, but this has some flaws, because of course if your application doesn't free the CPU, no other process will ever run. So there is another kind of multitasking which is called pre-emptive multitasking, which almost all operating systems, at least I know, support today, where the operating system actually interrupts the running program after a specified time slice. So it doesn't have to use, or the single programs doesn't have to cooperate. The operating system does the job and does a fair scheduling of the single tasks.
So in the context of multitasking and multi-threading, what are actually threads and processes?
Yeah. First we had processes. A process is a single execution unit, a program that runs in parallel to other processes, and there are a lot of features that a process has that makes it heavyweight, or let's define heavyweight a bit more. First of all, you have a separate address space. That means your program has its own address space and can't read or write the data from another process. There is a physical type in your CPU, which is most often called MMU, Memory Managing Unit, which does this protection. It actually checks if your read or writes go in your address space or not, and the application actually has the image, or it actually feels like you have your own address space complete, and the complete address space is just yours. This is a very complex thing in operating systems where the physical address in the memory and the virtual address are separated. That's pretty complex. But the main point is you have a protection of your process not to harm any other process that runs on the operating systems. The bad thing of this is, of course, context switches between these processes, and all the stuff you have to do for this is very expensive. Expensive in the sense of it costs a lot of time to switch the context between these different processes. And the other thing is processes, of course, have to communicate with each others because they live in the same infrastructure, and there is stuff they have to talk with each others. And this inter-process communication is also very, very expensive because it has to go around all these protection mechanisms. So there was this other thing called threads.
Yeah, threads are more lightweight than processes, and here the different threads run actually in the same address space, so they can access each other's data. They have all the data in common unless it's explicitly separated between the threads. OS designers invented threads after processes to have parallel execution of code within the same process. The bad thing about threads is that they don't provide any protection for data corruption. So if there's one misbehaving thread, it can corrupt the data of all other threads. The good thing about threads is that the context switch of the CPU, switching between threads, is more lightweight, is cheaper, and there are no inter-process communication barriers. The communication between threads is much easier, much faster. There are some differences in thread implementations between Unix and Windows, but nowadays you can say in general they are more lightweight than processes. There's a similar term related to a thread, that is task, and the term task is often used in the context of real-time operating systems such as VxWorks. And tasks typically don't have their own address space. In that regard, they are similar to threads. And one of the reasons they are called tasks and not processes is because they run typically on hardware that has no memory management unit. And so because of that, they have actually no chance to protect their address spaces.
Mm-hmm. Now that we have the operating system in place, which does all the multi-processing, multitasking, multi-threading stuff for us, what is actually difficult dealing with concurrency? Where are the problems?
Yeah, the hardest part and the most challenging is the access to shared resources. Those resources can be any devices of a computer. It can also be memory locations or the database. And the second hard part is how to achieve actually a performance improvement and not end up with a locked up application and dozens of hidden race conditions and corrupted data at the end. And the third hard topic is adapting to algorithms to work in parallel and to synchronize at the end of the parallel threads processes for the final result.
Okay, and how can we as programmers keep them in consistent state? What are the tools we got to do this?
Yeah, an important term here is the critical section. And in programming, a critical section is a piece of code that can only be executed by one process or thread at a time. And in that critical section, we actually access the shared resources. Another term and really elementary concept of concurrency are semaphores. They're not used so much today. Mostly in today's programming, we use mutexes and locks, which we will explain in a second. Semaphores are basically protected variables, and they allow to restrict access to shared resources. They manage the entrance of critical sections, and they are typically a pretty elementary way of OS implementations to provide synchronization between processes and threads. And the simplest kind of semaphore is a binary semaphore, which is used for just what I said, to manage the access of a single resource. And a binary semaphore is basically the same as a lock, or also called mutex. They're both similar concepts. And the lock is used in a way that when a thread once entered a critical section, it gets the lock, does something inside a critical section. When it leaves, it will release the lock again, and no other process or thread is allowed to enter that critical section while another thread or process holds the lock.
Mm-hmm. What problems might occur in practical programming applications with this stuff? Could you give examples on?
Yeah, one of the hardest topic and really painful problems is a race condition. A race condition happens when you have inconsistent data because of overlapping parallel executing threads, manipulating the same shared resource and leaving it in an inconsistent state.
Yeah. Yeah, and another, well, it's not really a different kind of bug, but what makes working with concurrency pretty hard is what we call Heisenberg Box, which means you have a problem, and if you, for example, debug the problem or enter some print lines in your algorithm, the problem disappears. So because your debugging or your logging or whatever changes the speed of execution, the problem is not, it disappears actually, so you can't reproduce it. It's still there, of course, because it didn't disappear, but you changed, the behavior changed because of you looked at it. So it's a bit like this quantum physics Heisenberg stuff.
Yeah, another hard problem are deadlocks. And deadlocks happen, for example, when a thread forgets to release the lock, or even more difficult when you have two threads and thread A gets the lock, asks thread B for something, and thread B also needs the same lock to answer the request. But thread B will never get to acquire the lock, and thread A will never get its response, the result from thread B, and deadlock. Nothing moves forward, nothing moves backward. The program just freezes. So, but why should I care about concurrency? In which domains do I get in touch with concurrency?
You have concurrency in all the layers, or all the layers you have to deal with offer some kind of currency today. CPUs do, they have multi-cores, parallel pipelines and all that stuff. Operation system offer concurrency, they have these processes, threads. Virtual machines actually do, an infrastructure like servlet engines, enterprise Java beans, whatever. There are a lot of, well, infrastructures like web servers that also offer concurrency. what is pretty comfortable, some of these hide the concurrency topics away from the developers. So as a normal EJB developer, you should not have to care about the concurrency stuff, because the concurrency is embedded in the architecture of EJB, so it's hidden away from you. So it's the same like if you write a very simple program without any concurrency, you don't have to deal with concurrency offered by the operating system, that it's a multi-user, multitasking operating system. It's just hidden away beyond. So concurrency is everywhere, and you have sometimes to deal with it, sometimes not so much.
Yeah, regarding application domains, we found 3 key domains where you have to do hardcore concurrency programming. The first one is developing infrastructures like application servers, component containers, where you want to provide some level of concurrency, but you want to shield also the component developers from all the concurrency difficulties. And because of that, you have to do all the work and keep the component data and the component state in a consistent state. Secondly, developing embedded applications, you are mostly faced with a lot of concurrency. For example, in the automation domain, when you control and monitor multiple devices, or an infotainment system where you have to gather GPS information for navigation, where you have to visualize the current speed of the car and provide at the same time entertainment functionality. The third big domain are databases. Databases are shared resources by nature, and here the concurrency is managed through so-called transactions. Transactions are in that sense similar to locks, similar to critical regions, where no concurrency or interleaving threads or processes should occur and manipulate the data.
Yeah, and to talk a bit more or specific about a concrete example, let's take a look at the Java virtual machine as a container. The Java virtual machine actually offers concurrency, and Java itself goes so far that it has some construct, the synchronize keyword in the language, that helps you dealing with concurrency. And synchronize is one of the stuff we we'll talk about one of the following episodes, I guess. Synchronize is actually an implementation of a monitor, which is one of these how do I protect my critical section things. But we will talk about this later. So the virtual machine offers multi-threading within the virtual machine, and it might depend on the operating system the virtual machine operates or runs on, but it also has its own implementation of multi-threading, green threads for the people who used it ever, where the virtual machine does all the scheduling stuff itself to be independent of the running on or the operating system it runs on. So if you deal with concurrency in the Java virtual machine, you actually might not really be sure which layer below does the concurrency, because sometimes or most of the time the virtual machine delegates the concurrency to the operating system, because then it can use more than one CPU. Otherwise, the virtual machine would be seen as one single process from the operating system, and so it can't be parallelized to more than one CPU. So it's sometimes important to know how the layers below, or the layers that offer you the concurrency features, actually implement concurrency to get the speed of your or the parallelism of your hardware you use.
Okay, that's it for this episode. We want to give a quick outlook of the next episodes. In the following episodes, we will talk about synchronization and concurrency in detail, what patterns are there, what are the best practices for synchronization and concurrency. And in the next one of the next episodes, we will also talk about how to build highly scalable servers.
This was another episode of Software Engineering Radio. The Software Engineering Radio team wants to thank Henning Pauli for providing the music, as well as Libsyn.com for hosting and bandwidth. For more information on the podcast, past episodes and feedback, go to se-radio.net.